off on because then it's done.
Yep. Cool.
And people should have received that. All right. So, okay. So we seem to be on time. Let's just wait one more minute. Yeah, somebody's asking why are we recording? And what I said a bit earlier is that we were not sure that we could, but as long as people don't turn on their camera and then come back and complain that they were recorded without their consent, I think we should be good. Okay. So welcome everyone to this session of Rebase. Rebase is a small event that is held twice a year together with the eCoop and Splash conferences. We had our first instance last year and it was virtual when eCoop and Splash were co-located. And this is the second time we're having this event. And yes, it's great to have you all here. So great pleasure to have the two following speakers. We have Rob O'Callaghan and Andreas Zeller. I've been trying to get Rob to talk at the conference for many years, but it seems that one of the advantages of these all virtual times is that it's actually easier to get him to show up. So I'm really glad. I've been following Rob's work all the way since '97 when he wrote a paper on Lackwit. Just that title was good enough for me. And then he was at IBM and Mozilla, and he worked on the RR debugger that, at least in my group, we use very heavily. So.
Wow.
So this is a great opportunity. And Andreas, well, Andreas has more distinguished paper in software engineering than I knew were available. And I've been also following his work all the way. I think so. The bit that I remember the most is the Delta debugging. That has been very influential. And he has written books on why program fails, fuzzing, and now debugging. So it's quite appropriate that we have both of you talking about debugging. So the format of this session, we'll have a talk by Rob, and then a freewheeling discussion between Rob and Andreas. Questions are welcome. So I think during the talk, type them in the chat, and I will read them to Rob at when it seems appropriate. I don't want to break the flow too much, but so I'll just use my judgment. And if you think I'm not reading your question fast enough, complain in the chat, and I'll deal with that. And at the end, we'll see. Maybe we can have live questions depending on the size of the audience and the number of how. All right. So without further ado, Rob. The floor is yours.
Great. Thank you very much. Yeah, it's a great pleasure to be able to do this. Thanks a lot for the opportunity. Right, so I thought today I'd talk about ubiquitous omniscient debugging, which is basically what would it take to make omniscient debugging something that is available for everyone, everywhere. And first I better talk about what we're talking about when we talk about omniscient debugging. Some of you may have heard of the concept under the name timeless debugging. The terminologies in this area is still getting a bit sorted out. So basically, traditional debuggers let you look at the state of the program at a specific point in time. And normal debuggers will let you go forward. You can execute forward until you reach a breakpoint, or you can single step forward. And if you've got a really good debugger like RR and others, you can do a kind of reverse execution debugging, where essentially we'll fake it so that you can actually, it looks like you're executing backwards in time, which is actually really powerful because, effects precede their causes. So when you're causes precede effects, right? So they happen before the effects. So you want to be able to go backwards in time to get from the effect of a bug back to the root cause. So that's great, but you're still limited to looking at a single point in time, and that turns out to be quite limiting. What I say we would really like is the ability to look at all program states at once, and perhaps visualize how something's changing over time, and basically break out of this single point in time view of the program state. And I'm going to show you a demo in a second that will, I think, really illustrate, hopefully explain why this would actually be useful. But before I do that, I just want to talk about the 3 pillars of omniscient debugging. The three big things we need to be able to do to make it useful. One is that we want to be able to access any program state at any point in time efficiently, right? We don't want to have to do a lot of work and make the user wait for a long period of time while we retrieve or recompute some program state from a different place in the history. I also want to be able to map that state and visualize it at the source level. That's actually really important and actually quite hard. So developers want to understand their program state at the level at which they're writing the code, not like just machine code or a raw memory dump. Another thing that's, I think, a really distinguishing feature for omniscient debugging is the ability to explore connections between states. So the ability to understand, for example, exactly what data flow happens, right? Like just a series of snapshots, you might not necessarily be able to recover how you got from snapshot A to snapshot B. And that's actually those connections are actually important. So we need to capture those. So to make these intuitions a bit more concrete, I'm going to show you a very quick demo of an Omniscient debugger that we've built in our company, Pernosco. So I hope you can all see my screen here. It might take a little while to snap in over my internet link here. And I think you can't see my mouse cursor. So I'm just going to have to talk through it. So this is the interface. You can see that on the right-hand side, we've got the source code, which is often what programs care most about. On the left, I'm showing just the output of the program. Now, if you look at the source code view on the right, in the margin, there's these orange blobs, these orange blocks next to source lines. Those indicate that line has been executed in this invocation of the function. Now, this is main, so there's only one invocation of the function, but in general, there could be more, right? So just by looking at these orange blocks, you can see, for example, that the errors, the fprintf to std error, pipe failed, that sort of thing, those errors are all have not been executed. So just by highlighting the lines that were executed with orange, we can see a good overview of the control flow of the program. We can do more. So, before I move on, I should mention this is an example of how visualizing state over time, I think, is really powerful. If you're in a traditional debugger, to get all this information, you would basically need to step many times and build up a mental picture of the control flow in your head. But because we have this omniscience, we can show you directly what's happened without you having to do that manual stuff. So I can click on this light yellow box here, which is executed 300 times. And if I do that, I get a list of all the executions of that line. We didn't have to re-execute the program. This came straight out of our Omniscient database. That's what Omniscience is about. I can also add conditions. So if I add the condition I equals 10, I just get the one execution of that line, which I can click on. And if I hover over I, it's actually 10, as you'd expect. So again, we're just exploiting this sort of database and just visualizing the contents of our database. We can do a little more that's interesting. So if I go down to line 200 and activate that. So there's this file descriptor called socket write fd. Its value is 7. If I click on it, I can get a data flow analysis of that value, right? So what's happened, what this data flow view is showing me in the bottom left is that it's showing me some steps that were involved in producing that value, that essentially the data flow through the program. So if I click on the last step, this is where the local variable was assigned from this fd0 element of this array. So that's one step, but I've got other steps here. So if I look at the second step, I can now see that now it's showing me that the socket pair call was actually assigned the value of FDs, and so and I can go back further and I can actually dig into how the C library actually initialized that. So that kind of data flow analysis is actually you can do a bit of that with existing debuggers, like with RR. You can use data watch points and reverse continue to get some of that information, but it's much faster and with an omniscient debugger like Pernosco, especially if you have many steps of copying and other operations that you want to scan through very quickly, which you often do in very large applications. So that's the end of that demo. I hope this gives you a really super high level, quick view of the sorts of things an omniscient debugger can do. And there's a lot more features that we have that exploit that. So one question before we go on is, does it matter? Like, if I give you the super powerful debugger, is it that much better than other debuggers? Does it really help developers? Is it that much better than RR, for example? And I've got some quotes here from users explaining how when they use an omniscient debugger, it really saves them a lot of time, even if they're already sophisticated RR users. So this is a Mozilla developer's quote here, which I hope you can read, saying that it's good. And there's another quote from a developer here who's using Pernosco and finds it a very large improvement in the debugging experience. So I'm going to claim and assume from now on that this is something that is important and that it will be good if everyone was able to do it. So one question that's going to jump into your mind very quickly for any computer scientist is it practical to implement something which stores all program states? I mean, obviously that's a big ask. And so I looked at some data we have for a recent session that we did where we processed a test failure in a Firefox media test suite. The screenshot on the right of the slide is showing you just part of the output of that test suite. So this test suite ran for nearly 19 minutes of real time. Now, we were recording it under RR in this case, so if we hadn't been doing that, it would have been quicker, but it probably wouldn't have been vastly quicker. It executed 1.5 trillion instructions, so it did a lot of work. And from that, we generated a 474 gigabyte database with all our omniscient data. And obviously, we're doing a lot of engineering to get to that level, right? If you do something naive, you're not even going to get close to that. And then to build that database took 108 minutes of processing, so under 2 hours. And that's on a mid-sized machine, so an AWS C5D9X large, which is 18 Xeon cores. If we throw the whole our analysis is extremely parallelizable. So, there are much larger machines out there now that can speed this up quite a bit. So yes, you can actually analyze fairly heavy-duty things and get results in this omniscient debugging. Okay, so anyway, what I really want to talk about here is, assuming that we do want to do this, what do we have to do technically to make omniscient debugging ubiquitous so that you can use it pretty much under all circumstances? Right now, Pernosco, for example, is limited to Linux applications, x86, 64, and certain programming language limitations. So we're going to talk about how to fix all those limitations, basically. All right. By the way, if you do have questions, I do welcome them because it's much easier for me to give the talk if I've got some kind of feedback instead of just talking to myself here.
Can I ask
one
question? So
absolutely.
In the case of an application that has is the size of the database proportional to the size of the data manipulated? I would guess yes.
It's really proportional to the amount of work done. The amount of work done by the CPU really is the limiting factor. Yeah.
So are there cases where it just
sorry?
Are there cases where it just up?
Performance-wise, not. The longer you run it, the more work there is for us to do, and the more data and so on. So if you just had a really huge workload that ran for a really long time, it will blow up. There isn't anything that causes like a performance cliff generally. If there is, it's just a bug that we can fix. There are certainly many things we don't handle, which I will talk about later, which do cause us to blow up one way or another. But performance-wise, it's fairly linear. Let's talk a bit about the design space of omniscient debugging, because it's actually quite large, and we're only exploring one piece of it. And I'll explain why we prefer the part that we're in, but there are certainly alternatives and other products and systems out there, which I'll mention. So the first part of the first design decision is, what's the level of abstraction that you want to observe when you're essentially capturing all this information? And we've chosen to observe CPU instruction execution. It's a fairly well-defined sort of thing, and it's kind of universal in some sense. you can also do this at a high level, and it has been done at a high level. So you can instrument your like a Java virtual machine to record everything that the virtual machine executes. And but of course, you only get the Java level. You don't get anything else happening in the system. And so, so Bill Lewis, who actually coined the term Omniscient Debugging a while ago, has built a tool for this called ODB, and there's a research paper from about 10 years ago, I think, called TOD, which basically does a similar sort of thing, but with more engineering. But yeah, so we're going to focus on the CPU level. And another question is sort of what instrumentation technique are you going to use, especially if you're going to do something at the CPU level. So one way to do it is to emulate the CPU, and you can just instrument your emulator essentially. And your emulator might employ some JIT techniques, or it might just be a pure interpreter. So there's this system out there, pretty well known. It was a research tool originally, I think, called Panda, which basically instruments QEMU's x86 implementation. And that's been commercial. There's a commercial product called TechTrain, which is probably the closest thing out there to what Pernosco does, for example, which is actually based on Panda. For Pernosco, we decided to do binary rewriting because we thought we can hit higher performance, and I think we do because of that. So it's basically taking input machine code, instrumenting it, basically doing your traditional dynamic binary instrumentation techniques. Another really important design decision is what's the scope of your instrumentation. So what are you actually looking at when you record stuff? Sometimes you can, in some cases, you can just look at specific libraries or components of software, like your application library, and ignore system libraries. You could try to do that. You could target a particular user space process, or in general, you could target a group of user space processes that might be interacting, and that's what we do. So Pernosco records a whole set of user space processes that may interact in various ways. You can also go further. You can record the whole operating system image and all its guest processes, and that's what something like Panda would do. You can also go further in theory, right? And you could actually record a whole cluster of machines and try to provide a unified debugging experience for that, which I think will be awesome. And there's another question of like, what do you do about things like GPUs, which are also executing code in your system? So sort of heterogeneous things. So that is a very good question that we don't have it. We have certainly a question we haven't answered yet. So that's another important piece. Another really important thing when you're designing one of these things is like, do you instrument the live execution of the program so that as the program runs, you're doing all your analysis essentially online? Or an alternative is to record the minimum that you need to record to get a replay. So essentially you bring in your record and replay technology like RR, and then you instrument the replay. And so essentially you can do your analysis essentially offline. And that is quite appealing. And one main reason it's appealing actually is because you can then parallelize the replay. So you can replay the program like 10 times with different instrumentation in each replay run, or instrumenting a different section of the program execution in each replay run. So this is how you really take advantage of big machines to build these big databases and basically use a lot of machine time to give a better debugging experience. So I hope that was clear. So let's dive in. So the issues, yep.
There is a question asking about something about binary rewriting. The question from Maurice is binary rewriting more error prone than instrumenting the emulation?
It's hard. It's probably a little. That's a good question. I don't know if I really know the answer to that because I've only done one of those implementations, not both of them. I think writing an emulator is going to be a lot more work than just in binary instrumentation. When you're doing binary instrumentation, we care about aspects of the semantics of x86, but we don't have to implement all of those semantics. So I think it's either of those things is much less work than writing the emulator in the first place. If you already have a high quality emulator and you just want to instrument it, that might work well. If you don't have an emulator already, I think you're going to do a lot more work writing an emulator than just doing binary instrumentation. Excellent question. I hadn't really thought about it.
Then there's another one in the chat. It is in the media test suite example, how much data was recorded during initial execution? So you said the database.
It's an excellent question, and I actually didn't get that number. I mean, I imagine it would be the order of certainly less than 10 gigabytes. Probably hundreds of megabytes to, maybe 5 gigabytes, something like that, I would guess. I'm just guessing right now. So I didn't collect that number from the data. But that's kind of a number you're thinking about. It's much, much, much smaller than the database we end up building. And that's really an RR question, because RR is our record and replay engine.
Thanks.
Okay, so the biggest problem that we have, I'll just lead with the biggest problem we have, which is basically handling parallelism is difficult. And the problem here is that we need to make this work with this offline approach where you do a record and replay and the instrument the replay. You need to be able to do record and if you're looking at parallel code, you need to do record and replay of parallel code. And in general, you want to be able to handle data races, right? So there are ways of doing efficient record and replay of parallel code that work if your program sort of adheres to a restricted programming model and it doesn't have any bugs that cause it to escape that model. But in general, of course, we care about buggy programs, and in fact, a lot of real-life code does have data races. They're kind of benign. They get fixed, maybe they don't. So, we do need to be able to handle that, and that is a problem. On commodity hardware, it's just not possible to do it, as far as anyone knows, with low overhead. So there's a lot of academic research in this area, and most of it works by relaxing one of those assumptions, which is unfortunate. I think we can make it work if we have access to the hardware. Like if we get instrument caches, then we could. I think there's things we can do. Intel had a really good look into this about 10 years ago with QuickRec, and I think they concluded it could work. But the economics are a problem, right? Like no one's going to do a TSMC run with this hardware in it unless there's a lot of money to gain, and this is kind of our problem right now. So there's a bit of a bootstrapping problem. Like if everyone believed today that Omniscient Debugging and record and replay were amazingly important, we'd probably get this hardware. But on the other hand, without the hardware, it's hard to say a lot of people that it's going to work. So it's possible maybe that we can get around this in the future by maybe having custom chips using open cores, maybe just doing a run and putting those things in the cloud so people can rent them instead of buying. That might work. And then supporting hardware, supporting GPUs, doing debugging of GPU code would also probably require something pretty amazing in this space. And I really know nothing about that, so that's kind of above my pay grade. Now, I do want to say that there are still some interesting design points that haven't been explored with commodity CPUs, some things that I think should have been tried that haven't been tried yet. I don't really go into the details, but we kind of skipped over a few possible solutions in that space. I'm not sure if they would work or not, and I don't want to do the research in case it doesn't work out. But it's not totally out of the question that you could make something work with commodity hardware, but we haven't made it work yet. So that's a big problem. I'm just going to put it out there. There are also hardware issues with non-deterministic instructions. Most instructions are deterministic, which is why RR works at all. But it's still a problem that there are some that aren't. Obviously, you've got things like random number generation, which would not be deterministic. And in many cases, we can get around this problem by trapping those instructions somehow. On Intel, we can intercept CPU ID and lie to applications and tell them that the features we don't like aren't even there, and that generally works. We do have some problems in practice. ARM, for example, has some non-deterministic instructions that are pretty fundamental to their atomicity model, which we can't really get around. Fortunately, I didn't put this on the slide, but newer ARM revisions have moved away from this LLSC stuff to things like compare and swap as a fundamental instruction for performance reasons, fortunately. And so newer architectures and platforms we can probably work on, which is okay, which is good. But then we've got other chips like AMD Zen where RR does work, but they don't have CPU ID trapping like Intel does. And so it's harder for us to guide applications away from problematic stuff. Those are issues. These are relatively minor issues, but they do keep us awake at night because these guys don't necessarily know or care about what we're doing. And so another big issue would be embedded. Like if you wanted to make this work, systems like RR and the whole Omniscient Debugging thing work because we have a lot of resource available, right? Like we have big fat machines, we've got lots of cores, and we've got lots of memory, and we can spend some of that as overhead to make debugging better. But when you're on like a very small embedded chip, obviously you don't have that kind of stuff, and it's going to be a challenge to put record and replay on there or something else. So I think for embedded, the long-term solution will be using an emulator or possibly a hardware platform that wraps around your embedded chip and is able to capture the environment and replay it and so on. So maybe there are ways to solve this in hardware that way. Again, embedded is not really my thing, so I'm just going to have to put that out there. So I think you kind of alluded to this before, but scaling issues are an issue, right? So if you run your program long enough, if you run that Firefox, if you're on a Firefox test suite that takes in half an hour, or 10 hours, I mean, eventually your resources are going to run out, and it's going to become implausible to do this omniscient debugging. And so for that, the ultimate solution really has to be to actually analyze subsegments of execution on demand. So if you could at least record and replay that stuff, we might not be able to build our big database. We might not actually be able to give you instant access to any state at any time. It's just too much of it. But we can probably do something that gives you a pretty good experience by essentially reproducing states on demand, and maybe using some really big machines to try to make that as fast as possible. And I think there's definitely interesting work to be done there. I don't know if we're going to be doing it anytime soon. Pardon me, sorry. So let's move on a little bit from hardware. So looking at operating systems, as you do, if you're looking at if you're debugging user space, which I think is a good idea, right? Like I told you that we reproduce and analyze groups of user space processes, because most of the time people don't want to debug the kernel. There's use cases for that, especially in like security, but people generally, our users don't really want to debug the kernel, so it's actually advantageous to ignore what's going on in the kernel. It saves a lot of work. But it does require a deep understanding of the kernel user boundary to make all this technology work. We need to know what the effects of system calls are. So when you do a system call, we need to know exactly which memory locations could have been modified so we can update our databases and so on. Now for Linux, this is actually pretty okay. We can dig into the source code, we can actually instrument the kernel, we can do all kinds of things to figure out what's going on, and we can even talk to the kernel developers if we have to. But for other OSs like Mac OS and Windows, which people constantly ask me if they can have RR for Mac and Windows, and the answer is no, because basically, only Microsoft and Apple can have access to the information that would make this at all pleasant. Right? I guess if I had infinite money and time and people, we could reverse engineer everything we needed, but we don't. So this is an issue, and basically this is really just about like, do the platform vendors care enough to actually do any work on it? Well, we'll see. So another issue is that, again, I guess it's sort of related, which is commodity operating systems were not designed to do record and replay or provide omniscient debugging. And we get it to work by using existing APIs in sometimes unintended ways. If you look at I don't know, if you care about this stuff, you should really read the AR paper for some of the gory details. But we essentially leverage existing APIs and in horrible ways. And it's also somewhat inefficient. So we've got our overheads pretty low with a lot of work. But we do have we have these user space processes that essentially are acting as supervisors. And sometimes you have to trap to them to handle certain things, and there's no way around that. Things like context switches, memory maps, they're hard to handle without context switching to a supervisor to do the real work. And those context switches are expensive, because context switches are always expensive. And so if you actually moved all this stuff into the kernel, it's just faster. I guess that's true for a lot of things, but it's especially true here. And I think it would be great if someone came, people said, we really care about the stuff and we're willing to do some work in the operating system to help you. That would be really nice, and we could do a lot better. We'd be more robust, and overhead would go down a lot. So that would be good. How are we doing? Okay, so I'm going to talk a bit about programming languages now. I know that there's probably more people interested in programming languages than there's other things I was talking about. So let's assume that we have CPU level omniscience, like Pernosco gives you. And I think you do want to assume that, because sometimes you do want to debug at the instruction level or the C code level, right? Now, it would be nice also to be able to debug high-level languages in the same debugger. One piece of feedback that we've gotten, which I think is interesting, is one reason people don't use debuggers is because they don't like learning a new debugger for each new programming language. So it would be actually a very good thing if we had a single debugger that could debug everything. That would make a lot of people's life a lot better. So sometimes, we need a debugger that can debug at the low level and at a high level at the same time. Now, to do that, you need to be able to map CPU and memory state to source level structures. And for statically compiled languages like C, C++, Rust, that sort of thing, there's this, there are ways to do that, right? So we've got this dwarf standard that describes, you can emit all this metadata that describes how to do that mapping. It's kind of solved. I mean, there's a lot of issues there. Actually, I could have a whole talk on why this is actually harder than you think and what needs to be done. But it's sort of solved. it's much less solved for complicated language virtual machines. It's very hard to go from the machine state to Java VM, Java level state in a multi-tier Java JIT, for example. And it's even less solved if you don't want to modify the virtual machine. If you just want to take an off-the-shelf virtual machine and do this in a product like we do, and you can't get the virtual machine developers to change their code to help you, then it's harder. So I'm going to show you what we can do.
Rob?
Sorry, yep.
Yeah, just a question, I think on a previous slide. Can you use the new BPFVM feature for more support on the kernel side? So
can we use BPF to? I'm not sure exactly what they're referring to with BPFVM. Yeah. I mean, yeah. Sorry.
So we can take it later on.
We'll take it offline and we'll talk about it, or maybe discuss it later.
And then
make it quick.
Another point
Yep.
From Dimitri, undo.io showed some really cool demos of mapping CPU level execution traces to Java source level.
Right. Okay. Yep. So they're doing something. Microsoft also has a similar sort of thing for their timetable debugger, mapping to C#. I don't know how this stuff works because it's closed source in both cases. It's probably doing something similar to what I'm going to describe, but I'm going to describe. So hopefully, what I describe will sort of cover what they're doing as well. But I don't know. All right. So let me show you quickly what we can do. I'll just switch tabs here. Okay, we're good. So close you. Now, we're looking at JavaScript code now. So the source pane on the right is showing you essentially the same sort of stuff I showed you before, but now it's JavaScript code. So you can see the control flow. You can see which lines were executed. I can hover over variables and get their values. Essentially, every feature that I showed you before that works for C++ works for JavaScript. So maybe that's a little boring. Maybe that's a little obvious. I'll just show you a couple of things. So I can get the executions of a different function. I can set conditions if I feel like it. Now, over on the left, there's a stack. Right? I hope you can see this. At the bottom, there's the func1 frame. Actually, I'll look at the second execution of func1. All right, so func1 gets there. It's actually called from this little script here, which is actually being evaled over here. And that's being called from this top level frame up here, which is doing everything. So, but I can go further up the stack, and now I'm looking at C++ frames. I hope you can see all these. I don't know how well my network's doing. But again up here, it's my C++ debugger. So it's not that I have two different debuggers. I have a JavaScript debugger and a C++ debugger. I have a single debugger session where I can debug multiple languages, this low-level code and this high-level code at the same time. And I think this is where we should be. It's where I want to be. Okay, so that's a super quick demo. I'm just now going to explain a bit about how that works. So it's essentially we take an unmodified V8 virtual machine. We haven't actually made any changes to it. It's essentially unchanged. And what demo I showed you is actually running in a stock in a Chrome build. So there's nothing really. We haven't done anything to it. We've disabled everything except the interpreter for reasons I'll talk about in a minute. And the V8 interpreter essentially works in a pretty classical way. You pass JavaScript source code to an AST. The AST goes into a bytecode generator, which generates an array of bytecode instructions. And then later on, when that code gets executed, there's a bytecode interpreter that plows through it. So the generator essentially generates this array, and also while it's doing that, it emits a whole bunch of records that map indexes in that array to source locations, like line numbers, essentially. Now, what we do, because we have this omniscient infrastructure already, we build on top of that. So we can essentially do a query that says, we look for executions of the V8 code that is emitting those records, or that emitted those records in the history. And then we grab those records from the history and copy them into our database. And one of the reasons we have to copy them into our database is because we actually have to build an inverted map. We have to be able to map from source locations to bytecodes. And then we actually associate our bytecode metadata with the address of that array that has been generated. Then later, the interpreter comes, we reach the interpreter. Now the V8 interpreter is implemented with each bytecode instruction implementation as a function that tail calls the next bytecode to execute. and calls and returns in our JavaScript functions are handled in a similar way. So, and of course, each of these functions has the address of the bytecode array and the index into that bytecode array and registers coming into that function. So what we can do is we can observe the executions of all of those instruction functions. Basically, we look at, it's like setting breakpoints on all of them and just getting all those executions. And then we get from the registers, we get the address of the bytecode array, and we can obtain, and we can look back basically to see where that was generated. We get the metadata that we worked out when it was generated. And we can then record the executions of bytecodes and function calls and returns in our database. So that was like a bit high level, but I hope that made sense. Whoops, that slide not supposed to be there. Yep.
How much extra work was it to support V8?
That's a good question. It probably was the work of about, altogether about 3 months, I guess, for one developer. Well, I mean, one developer who kind of knows this, knows this stuff pretty well. I mean, I didn't know V8 when I did the work. I didn't know V8 when I started. I mean, I knew about it because I worked at Mozilla, but I hadn't looked at V8 source code much at all. So it's not easy. But it's not like a PhD thesis. So there are some problems here. So bytecode arrays are actually moved around by V8's copy and garbage collector. So that's a problem, right? Because we need to be able to. We don't want to lose we don't want to lose track of where our metadata is associated with. So we have to actually also observe GC copy operations. And we do that in a similar sort of way. We look at the V8 code when it's executing the function that moves stuff. We just record what it moved, and we build a big map of where everything was over time, and so we can make these connections. A really interesting thing is that we handle data in a pretty different way. So we have written code that parses V8 objects from raw memory, and that's actually a bit tricky because V8 does a lot of optimizations. One thing I should mention here, of course, is V8 is a very, very sophisticated virtual machine. Where everything is optimized. So this is kind of the hardest case in some ways because, the virtual machine that you write for your research project is going to be a lot simpler than V8. It just has to be. So anyway, while we're capturing bytecodes, we're also capturing scopes and variable names associated with bytecodes instructions. So that gives us sort of the starting point where you can list all the local variables in a function and things like that. One thing that's interesting to note here is that we are explicitly storing JavaScript level control flow, but we are not explicitly storing the corresponding data information. The data values were always going back to the machine memory whenever we on demand, essentially. That's really because JavaScript control flow is kind of more abstracted in a sense because you go through this bytecode generation and interpreter process, which you don't really go through for data. So where were we? Yeah, so we want to support JITs. Of course, we want to support JITs, and right now we don't. So what would we have to do? Well, JavaScript engines have this kind of baseline JIT mode, and that should be straightforward to support because basically all they're doing is emitting, a few instructions for each bytecode instruction, and it's a one-to-one relationship always, because they basically care about this being very efficient to generate. So we can observe that code generation and remember the association between bytecode and JIT code, and then we can look for executions of that JITted code. That is not particularly hard. I think we could do this pretty quickly if we wanted to. However, if you go to the optimizing JITs, essentially they're doing the full-on, generate IR and then transform it like dozens of times, and it's pretty complicated. And tracking the way that bytecode's propagated through that intermediate representation is going to require some kind of VM corporation, I think. Unless they already do it, in which case, great, but I don't think they're going to do it very well, if at all. So this is a thing where I think probably our ability to make this work without any upstream support is going to run out. But I don't know, maybe not. Let me just say something. You asked about the development cost, and that was a good question. Another interesting question is, what's the ongoing maintenance cost? Because we are actually creating dependencies on V8 internals that were never meant to be dependent on, and they're absolutely not stable. So as V8 evolves, we do have to make some changes to our code. And our V8 support has existed for a bit over a year in a sort of at least a quasi-working form. We're able to do some useful work with it. And I think over that year, probably it's taken about 2 weeks of work for one of us to keep it up to date. So this is not too bad. And remember that, again, V8 has got a lot going on. It's always a big team. They're always making a lot of changes. So, again, this is actually a pretty good result, I think, and not less scary than I had thought when we started out doing this. Another really interesting topic is how do we extend this to arbitrary virtual machines and multiple debuggers? All right, like having developers for each debugger like do all this work and doing it for every single virtual machine that anyone ever comes up with and cares about doesn't sound like it's going to scale too well. So what we actually need is a common interface that debuggers and virtual machines can code to that will take care of this for us. And that interface ideally would be designed to support omniscient debugging well, so support us well. But it should also be, I think we can also get something that works for non-omniscient debuggers. Like if you just want to use something like GDB or Visual Studio or something, you can probably get that to work too. And I think the way that this would work, well, there's different ways of doing it, I think, but you can imagine, if you understood what we were doing with V8, you can imagine essentially doing that, but at a more abstract level. So the virtual machine implementation would essentially call stub functions to indicate that certain things are happening, like bytecodes are being emitted with certain source locations, or bytecodes are being executed, at the moment in the interpreter. And you can make this pretty efficient, I think, because at least for a record and replay based approach like ours, these functions don't actually have to do anything. You just need to make sure that the right parameters are available. And they don't even have to be explicit because of the way that Dwarf works. You can actually make them implicit. You can emit implicit metadata that describes how to get the values from the program state without actually realizing them in registers. And so I think we could make that work. I don't know if we're actually going to do this. It would require buy-in from virtual machine vendors, but I think this could be part of the future if we're lucky. Okay, so I've kind of zipped through all that. We've got time for more questions, but I just want to sort of put this out there that it looks like to me we can have a single debugging experience that provides omniscient debugging for everyone, all programming languages and all platforms. I mean, close, and we can dream of that, and we can get quite far towards that at least. And I've described at a pretty high level some of the technical problems that need to be solved. I think most of them are not especially difficult to solve. At least if you're willing to, if you're willing to do the work, if you're willing to do the engineering, especially the hardware side. And of course that would be expensive. So the real question is perhaps, well, now that if we believe that it's doable, the question then is, do we care enough to actually do it? And I think we should, but I know that right now we don't. So, but maybe that will change. Anyway, yep. So, yeah, that's pretty much it. Now, taking whatever questions you got.
Okay. Well, so a virtual round of applause. Thanks a lot for the talk.
No problem.
So what I would like to do is, before taking questions, would like to give the opportunity to Andreas to say a few words about the talk or his positions on debugging, and then I will take some of the written questions from the chat, and we'll see where we end up. So Andreas, do you want to?
Yes, thank you very much. Thank you very much, Jan, for having me here, and thank you, Robert, for all your so super exciting work. Absolutely. I say that I dig it.
Good, great.
Okay, so really, this is so exciting. I've been in debugging for quite some time now, and I think it was Bill Lewis. This must be some 20-something years ago who coined the term omniscient debugging, and I think he also built the first omniscient debugger at the time, recording everything such that you would be able to inspect things later. And at this point in time, the technical limitations were too big for large-scale programs, and I'm absolutely excited to see these things now really being done at scale and in a way that so many people can make use of it. Having said that, we're supposed to go in for a debate, and I don't think I can debate with Rob about anything, because the only thing I could, because my main concern would be, why don't we do more? And if I say, why doesn't Rob do more? I am not going to ask that, because Rob has done so much already. But you see, this was in 97. There was a cover of the communications of the ACM. This was the Debugging Scandal. And this essentially stated, So now for 20 years, we have done the same things in debugging all day long. It always was step, 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 print, step, step, rerun, step, step, print, and like things. And this is a situation which is daily inadequate and which needs to improve. Now things have improved. With RR, we can get rid of the run part, but we can step forward and backward. Well, it's a gross oversimplification, of course. But I still think that our debugging tools, as we have them, despite all the progress, are woefully underpowered. And given that, I think that's still the case, that programmers can easily spend half their time on debugging, and can still, and that debugging still is the most, not necessarily the most time-consuming, but the least predictable activity of all of software development, meaning that you don't know when you're going to find the bug, and this is why sometimes we have to sit there till late in the night with everything in our heads, all our hypotheses in our heads, all our observations in our heads, until we cannot be interrupted, because then we lose all our concentration and everything. Don't know how you debug, folks, but that was my experience when I did heavy debugging. So I still think that this is still a situation that needs to change. And while of course, simply being able to move through all points in time and observe everything in one single thing, this is great. This still means that we as humans essentially are focusing on one point in time, even though we can navigate freely across space and time in the execution, which is absolutely great. Our observation capabilities are still limited to the few data points that we're actually looking at. And then we have to compare those data points with what we think they actually should be. These are all situations for which computers were invented to take care of these repetitive and boring tasks. And this is something I would like, where I'd like to see much more research effort, but also more tooling effort. Well, sure, I can come along and say I'd like to see that. Yeah, sure. There's lots of things I'd like to see. I'd also like to see I'd also like to have a pony that produces rainbows. I would like to have universal health insurance, at least in certain countries, or I would like to have peace on earth for everybody. But let me focus on the small point. Let me focus on the small point here, that is debugging. You see, we could think about it. Given the enormous amounts of data that we can collect using RR, it actually shouldn't be too hard to also check all this data against our expectations, and that's something we spend far too little time on. How to actually automate our oracles, how to automate our checking here, because we actually can do that. The amount of data that we have in there that we can collect from executions is also something where where we also can search for patterns. This is a feast for machine learning approaches, figuring out which parts of the execution, which parts of the state, which functions executed whatsoever actually correlate with failures. And if you integrate debugging and testing further, you could even go and say, okay, now I have been looking at one execution, but how about generating additional executions in order to further narrow down specific hypotheses on the causes of errors, how to get further data points that I can go and associate things with. A simple thing. We're looking at one single execution and the program fails. So far, so good. And then we are using our debugging techniques to find out why this one particular execution failed. That's good. But then there's another step for which we have far too little support yet, and this is figuring out, are there other executions for which it fails? What is the generalization there? How do I precisely capture the set of executions that actually cause my program to fail? And I need to understand this, because this is also going to determine the scope of my fix later on. If I make the fix too narrow, then there will still be executions that cause the failure. Boom, then my fix is incomplete. If I make the fix too wide, then it may affect things that have been working previously. And these are still fundamental problems that are not addressed by debugging tools as I find them in commercial tools. They're not addressed sufficiently by tools that I can download, and they are still very, very open from a research perspective. From that perspective,
So
of course, from a researcher perspective, the glass is half empty, which is deplorable. No, sorry, it's half full, which is deplorable, but it's also half empty, which gives us as researchers which gives us as researchers plenty of opportunities to work on better automated debugging tools. Thank you.
So, thanks. I need to reply to that a little bit. So, I totally agree with you. I think that there is a huge space of work in that area to do. We've done a little bit of it. We've done a few things that I haven't shown you in the talk. For example, you mentioned one thing, which is keeping track of your debugging session, like forgetting everything and sharing what you know with other people, capturing your debugging knowledge and sharing it with others, I think is a really big deal. And we've actually seen that happen. We've got a feature in Pernosco where you can essentially take notes of data and where you are in the time stream. You can say, well, we're at this point, and certain invariants hold or don't hold, and you just record that, and other people can see those notes. They can jump to those states and inspect them, check their expectations, things like that. It is still fairly low level, and part of the thing is here, basically we feel like we have to walk before we can run. Like we have to get all the data. We have to build up on, with what we know, or what we think we know actually, is really valuable, and then try to do more exploratory sort of stuff. But absolutely agree with you about the importance of doing those things. I think I showed you some quotes early on that show that the features we're providing now do dramatically speed things up. People talk about a bug that would have taken them 5 days to debug, now it takes 1 day. Now the question is, how do we get it from 1 day to 10 minutes, right? But yeah, so big steps, we made some big steps. There are still big steps to take, which is also good and bad. About those steps, machine learning is obviously going to be relevant at some point. But I kind of feel like we haven't reached quite that point yet with Pernosco. Like, I think there's still productivity improvements that we can do that don't depend essentially on heuristics, which I think is my view of a lot of machine learning. Is kind of automatically learn heuristics. We haven't quite reached that yet. The other thing I would say is, in my mind, the biggest single issue which needs to be, we want to explore, which we would explore next in this space, is understanding the difference between different program executions. And I know that you've thought about this a lot, and so we should really talk about it more offline. But Pernosco, I feel like my understanding is that Pernosco are very powerful at understanding why something happened. They're not very powerful at understanding why something didn't happen. And that is there's no way to set a breakpoint on the function you can't set a breakpoint on the function that wasn't called that should have been. And so that is the problem that I really want to understand, soon. Hang on. So I would say, that's basically it. I think, and that I think involves comparing multiple program executions. So we really do need to figure out how to do that. I haven't figured out how to do that yet. So yeah, I hope that helped.
So maybe we could take some of the questions from the chat, and both of you can answer. What I would say is I'll read the question, and if the original, the person who asked it wants to chime in by audio, please feel free. I'll do my best to read them accurately. So the first one we had was from Alexander, and he was saying, and this was early in your talk, he was saying that recording everything is fine when you have no idea what you are looking for. But in many practical cases, you do have a rough idea what would be the entry point of an analysis. For example, it's not loading the video, but playing it, that's the problem. So what about having a way to roughly specify what has to be recorded rather than recording everything, I guess?
Yeah, maybe. I think that adds complexity. You have to figure out how you're going to get the user to describe that to you, and they're going to have to learn how to do that. And I'd rather not, right? Like if we have to do that to get scalability in some situation, maybe would want to do that. But it's really powerful to just say, look, just run this command and we get everything, and it's all you'll ever need, and you don't have to learn how to do these scoping steps. So it's kind of, that would be a last resort, and I think we're kind of looking for things that we can do that don't require, that aren't last resort things. Yeah.
So thanks. There's another question from Oscar, who's saying there are easy and hard debugging problems. The hard ones are when information you need is no longer on the stack. This is where Omniscient Debugging can help. My question is, can you use this technology to answer things like, where did this object or value come from?
Yeah, I mean, it depends on the exact answer depends on exactly what you mean by come from. But like, we have this data flow feature that I showed right at the beginning, where I can, we can track how a value was copied through registers in memory from source to sink, through many steps of copying, which is really helpful. So that addresses some set of those scenarios. If you're interested in example, like, where was the value constructed? You can search for the construct, we can search back in time for the constructor call with a particular, object pointer that was initialized, and that kind of works in C++. And there are more sophisticated variations of that we could easily implement. So like, when did you last call a function that returned a certain value? That sort of thing. In fact, you can do a lot of that today with our conditional searches. So yes, I mean, I think we can definitely do that, and pretty much, I don't know if we cover all possible interpretations of that question, but I think we probably could if we did enough work. Yeah.
All right. Then there's a question for Andreas. Nico asks, you mentioned using machine learning and large databases of execution traces to try and bring the engineer to the right point in debugging. Instead of doing the whole steps, print and step rerun dance, what about the debuggers that use completely different user interface metaphors, like displaying the program's data flow in this specific execution?
Definitely. There have been quite a number of very nice approaches over time, which I personally consider, likely superior to what we currently have in debuggers. This has not been established sufficiently because we need more user studies on that. A simple thing is, for instance, the work of Amico. That's a good question. When this was published, she was still named Andy. This was on the Y-line, the Y-line debugger, where you would be able, for instance, to see a particular event which you considered wrong, and then you could ask the debugger questions on where did this value come from, and the debugger would neatly highlight that out as a sequence of events that would eventually lead to things. In my own work, I've done some work on isolating cause-effect chains from programs that would also display important events that would, as established through real causality, would eventually show you that this particular sequence of events actually was causally determining the one failure you saw. A simple thing is also, this is also something that we've done years ago, is that you can go and take a particular object in your program, and then you can look at the calls that go into this object and determine its state, and then you can reduce the set of calls into a minimum that actually reproduces the same thing, and then what you end up is a unit test that consists of 3-4 calls that immediately reproduce the failure. And of course, this is far easier to debug than looking at the program in its entirety. So in our latest work, what we're doing is we're trying to find abstractions for inputs that determine when your program goes wrong. So if you have a calculator, for instance, which fails on whatever 2 + 2, then our tool is going to tell you, well, this actually happens for any expression plus any expression, so you know under which conditions the failure occurs. So all of these, so there are plenty of ways that we can come up with much better diagnosis. The assumption for many of these, however, is also that you're able to rerun your program at will, which is not always the case, and which comes with quite some setup. It also typically requires that there be an automated test, possibly even an automated oracle. Of course, these are great to have, but not necessarily part of a debugging setting. But the interesting thing from my perspective is, I and others, we can come up with great tools under certain assumptions, and assumptions that actually should not be too far-fetched. The interesting thing is why don't these things ever make it into your favorite IDEs? I mean, it's why do we have plenty of interest in why do we have zillions of researchers working on formal methods, PL verification and whatnot, but we have I don't know, maybe two handfuls of researchers who work on debugging, despite it consuming 50% of the time. We have workshops on everything, but we don't have research events devoted to debugging at all. That's the big mystery here. And at my point, maybe debugging is a dirty little secret. Everybody does it. Nobody wants to talk about it, and this is why we are stuck in this situation where the cool verification and testing methods we have are still not let us go free from debugging as we do it.
I'd just like to respond to one set of issues that you raised earlier, Andreas, which is about entirely different user interface paradigms for debugging. I mean, one of the problems that we have to grapple with is programmers know a certain set of things about debuggers, and it's hard to get them to migrate to something completely different. In fact, it's hard enough to get developers to use debuggers at all, the ones who are used to just doing printf debugging, essentially. But the ones who do use debuggers are used to using things like GDB, and presenting them with a completely different paradigm is challenging to get adoption. So one of the things we've worked on with Pernosco is trying to bridge that gap. And so we actually have GDB integrated into it. I didn't show that feature. You can fire up GDB and do whatever you want, and it's all synchronized with the rest of the interface. So we've got some pretty powerful features for examining things like data flow, but it's also the other stuff is also there, and some of the concepts that we currently provide do map onto sort of traditional debugging concepts. So the idea is that developers, and I think we see this in practice, that developers will come to Pernosco with a particular set of debugging strategies that they know, and those will still work. And over time, you will learn new strategies with the new features that you have. And I think over time, we can add more features that will veer even further away from the traditional paradigms. But I hope that we can integrate them into our all-consuming, tool, which does it, and which, apart from being sort of self-aggrandizing, will also mean that that developers can find a way to actually discover these things. One thing that we haven't really done, but we could do, like all your traditional dynamic analyses, like finding undefined behavior or Valgrind type stuff, ASAN, all that sort of stuff, TSAN, thread-based detection, any kind of dynamic analysis you can imagine, just about, could be rolled into Pernosco, right? Like, or another Omniscient debugger. So you could actually provide those results in the context of our system, or a system like ours, and then you can use the debugger to sort of dig deeper into what happened if you care about the details. So, so I think these things actually be integrated pretty well. I think we could actually build. It's kind of natural to see how you would build a kind of a universal dynamic analysis platform around a capable debugger that actually does a lot of different things. So I'm not convinced that we need to sort of disengage, like skip to a completely discontinuous interface paradigm and go there. I think we can actually integrate a whole lot of stuff into a single platform.
Right.
Yeah.
So there was, let's see. There were a few questions about concurrency and data races. So maybe I can take those. So Nico was talking about data races and non-determinism, and was asking, what about relying on language support rather than hardware support? I think you may have touched this in some way by talking about how to support V8, but generally speaking, would that be an approach?
Again, I'm not sure exactly what they might do. If you're thinking about something like Rust, which is supposed to be data race free at some level, that would probably be an example of that kind of thinking. Or JavaScript. Yep.
The question had an extra bit of information. Would it be possible to inject instrumentation exactly at the points where, at interesting points during compilation, and rely on replay for all the deterministic sections? Yes and no, right? So there was actually a project, I forgot the name of it,
but we'd actually aimed to do a record and replay system based on this. So there was a clean compiler plugin that would add instrumentation to all the operations on atomics, and then and they would hand instrument all the sort of C library locks and so on. So that means that if your program didn't have data races on non-atomics, which you shouldn't, then you would be able to do record and replay. And that was for C code, so you have no real guarantees that the language at the language level that against that. But obviously in a better language, you could sort of guarantee that at that level that there aren't uninstrumented accesses to racing data if you have the right sort of model. The problem then is you have to debug, like you only get record and replay for that level, right? You don't get all the way down to the CPU, because at the CPU level, you won't have that information. There'll be third-party libraries. There's always some C library in your address space screwing things up. So you're going to be stuck at the kind of high level. You won't be able to get out of there and debug other languages and so on. So it's a bit limiting from that point of view. It would be a good solution, in some cases, but it's not really the road that we would want to go down. I would also mention that these assumptions change over time. Like JavaScript was single-threaded, then we had web workers, which are kind of multiple threads of message passing. Now there's web workers with shared array buffers. So JavaScript has atomics now. The JIT compiler generates atomic code on the fly, so you can't do a compiler plugin-based thing that works with that unless you do one for each JavaScript compiler and keep it up to date like we do. So you kind of make these assumptions and then they get defeated later on, and then where are you? So that is what that's true for us too, right? We're making these assumptions about hardware. So there's risk everywhere you look, but it's a risky business either way.
And another added question by Gerald. Could data races be detected during record or replay? This way debugging could be done in two phases. First detect races, similar to TSAN. Then once there are no races left, Omniscient Debugging could work with multiple threads. People have suggested that. A lot of the debugging, a lot of the record and replay techniques that assume no data races will actually work up to the first data race and then explode. And then you can imagine doing some analysis that lets you figure out what that first data race was and fix that and move on. I think that might work, but it's really scary because like the programmer, how many data races is the programmer going to fix before they decide it's faster to fix their bug, the real bug, the one they get paid to fix? Some other way, right? Like if you have to fix 20 data race bugs before you can actually use the tool to do what you wanted to do today, that's probably not going to be very successful. Yeah. So now there's maybe back to the discussion we had earlier. There's a point made by Dmitry. Says the biggest problem is not that debugging tools are woefully underpowered, but that the existing tools are woefully underused. Even in situations when great tools are widely available, many people just log things and stare at logs and don't want to learn other approaches. And I think on top of that, I will add, generally a question that I was asking myself is how should we teach debugging? What are the principles that we want to teach?
Both of us are sighing. So
I think I'll let Andreas. I think Andreas should answer the question about teaching. I think that's totally up his alley, and he's going to be much better at that. I will say one thing about teaching though, which is that my son is at university now, and he doesn't use a debugger because he can't use it in his exam, his written exam, and he doesn't want to learn a technique that he can't use in his exams. What's the point, right? Why would you want to learn something you can't use in the exam? So that's one thing. About the first, and the rest I'll leave to Andreas about that. The other part was the question was about why do people use print debugging, and this is definitely a very, why do they just use print debugging? They don't use better tools, and this comes up all the time. And I think honestly part of the problem is that compared to traditional debuggers, print debugging has some big advantages. Like it gives you a picture of what happened over time, and it gives you that in a persistent way, so that you don't lose all your state when in your debug. You don't step too far, and then lose everything, which is a traditional debugger problem. You always have the log. Traditional debugging works in a distributed environment, works in the cloud. Log-based debugging. You can get a log from a remote machine, download it to your laptop and analyze it. You can't do that with most traditional debuggers. So I think a lot of these problems are actually fixed by the newer debugging tools. So something like record and replay tools kind of address the cloud problem pretty well. They address the reproducibility problem. You don't lose your state. So that's good. The logging thing, The ability to get a view of stuff over time, that is something that I think address pretty well in Pernosco. So I think we're getting a grip on some of those issues and I think we're finally making debuggers that actually are better than print debugging. But it's also true that print debugging is easy. There's a low barrier to entry, and it works in all programming languages. And that's just how it is. It's not the best tool in the long term, but it's the path of least resistance, and that always gets a lot of users. And there isn't really anything we can do about that as far as I can see. Now, Andreas can go now.
Well, why don't we teach debugging? Because why don't we learn debugging? In part because we're not supposed to do because we're not supposed to create bugs in the first place, and because there's far better techniques available that simply avoid us creating bugs in the first place. That's how I learned it. It's at university. I remember we had a lecture on Hoare logic, and here comes the precondition, then comes the statement, then comes the postcondition, then came the demonstration that we can actually prove that this is correct. Of course, there were no loops whatsoever, or the loop invariant popped out of nowhere, but well, so be it. And then we had these 5 lines of code, which now were verified. And this were how, and if only everybody would do it that way properly, then we wouldn't have to debug or test or whatever at all. That was all I had in all of testing and debugging for the matter. Simply pointed to formal verification will solve everything. Now, formal verification in the meantime has solved lots of things. So I'm actually amazed at the many progresses that have been done there, and our programming languages get better, and our programming languages prevent lots of errors. And in all generality, I think it's better to prevent bugs rather than to fix them later. So let's just state this. But the fact that even today, so I think that today students get far too little experience with testing, and even modern testing tools, systematic unit testing, fuzzers, simply generating lots of tests. That's not something, that's not rocket science. That's something you can teach in 90 minutes. So give them more insights on how to test systematically. And the same goes for debugging. I don't think that any programming course I've seen actually devotes lots of time to debugging, except for telling people, here's the log statement, so go ahead, find out what's going on. But there are really important things that you can teach, essentials that you can teach in 45 minutes. Things like use assertions, use assertions to check your stuff. Things like use a systematic process, use the scientific method, come up with a hypothesis on what this thing could be, come up with a strategy to observe things using omniscient debugging or a log statement or an assertion or whatsoever, and then find out whether your hypothesis held, come on, refute it, refine it in a systematic way, possibly even jotting things down, such that you're not simply staring at lots and lots of logs and trying to understand what's going on, and then you try this out again with some other value, comes another 1,000 lines of logs that you have to go through. No, you have to make this a systematic approach. And we know far too little about the performance of debugging strategies, what makes a good human debugger versus a bad human debugger. I'm sure that as with programming, the performance differences here are a factor of 10. And yet, I think that while it takes months to years to really become a master programmer, there are few little steps that you can, where you can turn anyone into a master debugger in the first place, simply by going through, by trying to find out the causes in a systematic way. And no, we don't teach that. This is not covered in textbooks. There's a huge book by Ian Somerville on how to do software engineering. It has one single paragraph on debugging, and this essentially states use the force loop. So, use your intuition to find out where the bug came from. I could have come up with that. But this is stuff which we really should teach. And as I said, 1 hour could already be enough to carry out to get you acquainted with the most important strategy.
But don't you think that one of the challenges for teaching debugging is that, unlike programming or proving, where there is an artifact that you build, the process of debugging is to making up a mental model of a program, but we never explicit that mental model. There is no, my debugging state, and therefore it's harder perhaps to teach that, because it's all about, making, very quick hypotheses that get thrown away but not recorded. No?
Yes. The exact fun thing about debugging is that you have a discrepancy between the mental model of the program that you have, that is what it should do, and the observations you make, that is what it actually does. Yeah. Okay, so there's a mismatch there, and in principle this should not happen. In principle, your program should work because, so you could simply go and say, I'm going to reinvent reality at this point, and I'm simply going to assume it wasn't there. But in the end, you have to resolve this, which also means that you need different strategies here, because you need to figure out where is your implementation or what you observe, where doesn't this fit the mental model that you've seen, and this requires different thoughts, and this requires different strategies than building a mental model, because you have to debug your mental model. But it's precisely these strategies that we don't teach enough. Whereas, as I say, a simple introduction to the scientific method, which was invented to find out what the sources of phenomena observed in nature are. You find out, oh, this block is heavier than others. Why is that actually possible? And then you make more observations, you come up with more experiments. Hey, this is heavier, maybe half of it is only heavy, or maybe there's a part of it that is heavy, or whatsoever. You can come up with all sorts of experiments and find out what's going on. And this is precisely the same amount of reasoning that you also apply to programs. But for this, you also need appropriate tools, you need the information, you need the ways, you need ways to make these observations, you need ways to make these experiments. And of course, this is where something like record and replay debugging comes in super handy. As I said, this is absolutely crucial. But we also need. I'm sure that half of the graduates of our university don't even know how interactive debugger works, or what a breakpoint is as a starting point. They know printf. I'm sure about that.
Oh. Rob, you seem to sigh.
Yeah, I kind of lost track of what the question was.
So one thing maybe I can sort of try to connect what Andreas was saying with Omniscient Debugging. It feels like when you debug, you make all of these hypotheses. You don't test them, you don't check them. But if you have the syntax for expressing those hypotheses, you could put them in an Omniscient Debugger and have the Omniscient Debugger evaluate them automatically.
Yeah, I mean, absolutely right. So I will say, we do have this notebook feature, which actually is there to start capturing your debugging state. I think it's what is the way you originally phrased the question. Is that, when people are debugging, they sometimes you take notes, but the state is very ad hoc, and it's it's not captured in an artifact that you can share. So that is something we have addressed. We're starting to address that, and I think we do need to add, like, for example, in the notebook, you can put variable values in there. So you can say, like, here's an expression, and you can write comments, and the expression is evaluated in the debugger there, and then you can say, here are my comments. You can type in like what you expected. So you can imagine going a bit further and actually typing in entering your explanation as a machine parsable expression. Sorry, your expectation. Entering your expectation as a machine parsable expression, and then having that be checked. I mean, we do have. I think I showed in the demo right at the start. Simple conditional breakpoint stuff. So there's a function that gets called. Here's an expression in terms of its parameters, even included, and its result. You can check its result there as well, even though the result happens at a different time. That's fine because we're omniscient. So you could actually do things like you could search for add calls to the add function where it returns something different from the sum of its two parameters. So we can start. We are able to do some very basic stuff like that now, but certainly we could do more. You can imagine doing temporal logic sort of stuff. I mean, that would fit pretty easily into our evaluator because temporal logic's easy when you're omniscient. So there's a lot that we can do, without much effort, to be honest. It's really a question of priorities. I mean, one meta thing that I think I want to make clear is that there is a huge amount of stuff that we know how to build, and that would look really cool. The question is, which of those things is actually the priority, and which of those things is actually going to be on the optimal path to finding bugs in real cases? So, and that's something we're kind of exploring with our users, right? Like, in a kind of incremental fashion. So, we kind of because we are very small, we don't have much resources. We are being quite cautious about how we explore that, but it is very exciting. That there's so many opportunities to do that, and yeah, that would be great.
So maybe any other questions? I lost track which ones I did. So if you have questions that are not answered, can you sort of either repaste them or type new ones in the chat? And
I have a question from Oscar here. Has anybody done any research to understand which kind of debugging problems arise frequently?
Yeah.
Rob, do you know what happens? Do you know what are the most important problems that you see?
I mean, I don't know if any research has been done, and I wouldn't call my intuitions research. That's something I refuse to do. I mean, like a lot of problems are, let me think. Yeah, I'm not even sure I know how to begin answering this. I mean, there's a lot of language-specific problems that are quite hard that involve things like memory corruption. Where essentially all your invariants can be defeated by any piece of code in the program. So and this is really the problem with sort of non-memory safe languages, right? And because all our customers right now are using C++, well, Mozilla is using some Rust code, but so memory corruption bugs are a big problem, and obviously, and RR is very powerful at fixing those. Like I don't know if they're the most common, but that's where a lot of people find RR and Pernosco to have a huge amount of leverage. Like it can be really difficult to track down, and with RR in Pernosco, it's pretty simple, right? You observe that some memory location is corrupt, and you set a watch point as to where that was overwritten. Sorry, what?
That's okay.
Can you hear me?
Yeah, the sound went a little bit bad.
You got me?
Yeah.
Okay. Sorry, I don't know. I hope I didn't break anything. So your memory corruption bugs are, I don't know how common they are. They are common, and they are very easy to track down with these newer tools, and not easy to track down with traditional debuggers. I mean, ASAN and stuff like that help you a bit, but not always. They don't always catch what you care about. So, and that's a bit language specific, but it's very powerful. And I guess there's other things where it's not a traditional memory corruption, but it sort of has the same effect. And I've talked to people who, I think, people who do research on garbage collection. Some of them have used RR, and it's really been incredibly people have told me that it saved them literally months of work, for an individual person. So that's really encouraging. I don't think that really answers your question, though.
I attended a talk at Facebook in London 18 months ago, and they have a group that does automated repair, which in a way is the continuation of automated debugging. So there's techniques which automatically suggest patches to you right away, which is pretty cool, or at least could be pretty cool. And this was Satish Chandra from Facebook, and apparently at Facebook, if some test fails, their technique automatically synthesizes a suggested patch. And if I recall the numbers right, 1 out of 3 patches was of the form if p equals null, return. So if there's a pointer coming in, then we immediately return. And this, lo and behold, has reduced the number of crashes in their mobile app tremendously. In particular, null pointer exceptions don't occur anymore. I guess there also should now be a certain loss of functionality in certain points, but
that's terrifying. That is terrifying.
It's a bit terrifying. And actually, Oscar is seeing the same thing here. The most bug fixes in open source Java projects is precisely that. If per pointer equals null, then return. There's now GitHub Copilot, which also suggests code to you, and I'm sure it's going to suggest patches to you very soon. And obviously, if p equals null, return is the universal patch for everything. Or why don't you just insert a return at the beginning of your main function, and then nothing will crash anymore? But yes, this is of course another thing. I mean, it's always tempting to fix the symptoms rather than the cause. Where does this pointer come from, and what does it actually mean that this is null? Does this mean that something has gone horribly wrong beforehand? That if I just mask the whole thing, well, then my immediate problem is gone, but there would be something looming under the hood for some longer time. And then that's also something. There's this website, the Daily WTF. Well, yeah, sure, you've seen plenty of people fixing symptoms rather than causes. And yeah, it's good for the metric. It fixes the unit test. Your bars become green again. Everything is wonderful. But so this is also something
I would say that
we need to train people better.
I mean, I think we all wish we had better information about debugging, like what people actually debug, and not just more data that's not anecdotes. I think one of the things that we want to do, like we provide.
We've lost
you anyway. Have more users, I mean. So that's something I would like to be in a position.
The sound is, at least on my end, the sound is going. Can you hear, Andreas?
No, unfortunately not.
We lost your last comment, Rob.
Sorry, yeah, my thing dropped out. I don't know what. I was just saying that we provide debugging as a service, and I think there's not many of that or much of that around. And one of the nice things about doing it as a service is you get all this nice data, and so we are able to collect some of that data. We don't really have enough users to, I think, say a lot yet, and we haven't got enough people we haven't got the resources also to analyze that data. But it's something that we desperately need as an industry.
One thing that just comes to my mind is it's actually difficult to do research in debugging. Because, well, look at our standard research methodologies and when we evaluate whether something works or what doesn't work. You come up with a verification technique, come on, you go ahead and you prove that it's sound and complete and has nice semantics and everything. You come up with a testing technique, you run it on a benchmark of your choice, and if it doesn't perform as you like it, then you twist the knobs until it finally works, which is what I frequently see in fuzzing papers these days, or what I at least suspect. And they have a benchmark, and there you go. But if you invent a new debugging tool, okay? If I invented record and replay these days, okay, then I could say, okay, here's record and replay, and it is performant, and it actually allows me to work with full-fledged Firefox sessions for 15 minutes. And then invariably some review would come along, yes, but does it help? Or actually, why don't I just restart Firefox? Or why isn't Firefox more modularized? Or why don't you just re-implement all of Firefox in Rust? Or actually, I've heard it's all Rust. Why do you debug at all? Or whatever. Okay? And invariably, so I have to run into these arguments. And then I go, okay, good. I'm going to resolve this thing, and I'm going to throw in a couple of $1,000 extra, and I'm going to run a user study. There we go. Here's my user study. And what I find out is, so here I do a user study with 100 people that do, half of them do with RR, the other does without RR. Well, invariably it turns out that in my group of 100 people and the control group, there's going to be people who are 10 times or 20 times as performant as others, and they will find the bug no matter which tools I give them. And others who are, well, not so great in debugging things, and if I give them RR, they're going to study the manual for 1 hour, and then they still won't understand how to use it, because they will be terrified at the simple fact that they see a command line and they don't know what to do with it, and they have to look up what a breakpoint means and whatnot. And it's actually, given our current publishing incentives, it's actually very difficult to come up with new tools and approaches. The best thing you can still do is, well, I'm tenured. I can build tools in my spare time. I can crank them out and let the public decide whether it's useful or not. Yeah,
I mean, I told Alex Aiken and I had exactly the same conversation 20 years ago. It's kind of sad. Like, I told him I wanted to work on debugging after I graduated, and he said, "Well, that's great, but I don't know how to." He said, "I don't know how to write a debugging paper and get it published." And so that was a bit discouraging. I think that's just absolutely a problem. I mean, that's why kind of in my talk, after I talk about, what we've done a little bit, like I just kind of give some quotes from users who are saying that they experience what they experience, that they experience these big improvements. And it's pretty unscientific, absolutely unscientific, but we don't have a better approach, I guess. So I don't know what to say, except it's very sad.
So something I always suspected also was such as if I'm a big company and I'm a manager at some company and I want to convince my own manager invest in testing tools, and then she's going to say, "Oh, are you going to find more bugs with that?" Of course I will. Okay, good. Here comes, and then I may make a case out of it. But if I come and say, if I come and say, I'd like to invest into better debugging tools, well, am I going to get money for it? Because this would actually require my superior to admit that there's bugs in the first place, and there's many bugs, and we spend too much time on them, and it's simple admitting that you're having bugs and you need to fix them. That's apparently that's not something that people like to talk about. It's like I may just go and say.
So let me talk a bit about this.
I need more detox courses because all my programmers are drunk all the time.
Yeah, I mean, this is something that is very.
We're losing
that.
The sound went out.
You can't hear me? Can you hear me now?
Yeah.
Can you hear me now?
Yeah.
Okay, sorry. I was just saying this is a very critical problem to us, because this is exactly what we're trying to do, is to sell debugging tools to exactly these people. That is true, I think, for most places. Can you guys still see me? Because my video is kind of sketchy. So what can I say? I mean, it's not universally true, right? I think it's true in a lot of companies that they're not interested in debugging. They see it as something that programmers just do, and it's inevitable. And our programmers are already fixing bugs. Why do we need tools to do that? They're already doing it. That's an attitude. But we have found some people who think differently. I think some companies have groups of people in them whose job is developer productivity, and I think they understand. Well, some of them do. Some of them understand that debugging is important and that they can improve developer productivity, and they have been interested in paying money to do that. So it's not a lost cause, but on the other hand, Pernosco is far from wildly profitable at this point. So I can't tell you that we've cracked it, but there is some. I think there is some hope. Otherwise, I wouldn't still be trying to crack it. Well, I guess the other thing is I have heard that debugging problems in production is potentially more lucrative than debugging problems in development. Like in development, problems can be hidden, right? There's all kinds of things you can do to ignore the problem, make it go away. But production outages are hard to hide, and there's more money in production as well. Like there's operations people who have all the budget. So I have heard that's the way to go. Now our technology, what I described to you in terms of what we're currently doing, it doesn't really reach into production unless you've got a single-threaded application server kind of thing running on Linux, which not most people don't. And there's some, but most people don't. So to be able to do omniscient debugging of production issues, we actually need to expand in some of those directions that I talked about in the talk.
So I have one question that has been there for a bit from Matt, which is cool. So Matt writes, can similar debugging to V8, from running JavaScript to C, jumping from the JavaScript to the C++, be done for compilation to execution processes for C or C++? Say, recording compilation with Clang together with the subsequent execution of the produced binary to be able to step back during replay to a Clang function that compiled that instruction and thus debug miscompilations.
Let me say one word here. If you ever wanted to know why people use printf debugging, this is the answer, because there's a printf in every language and it just adds to the log. Yeah. But Rob, what do you say?
I mean, I hope you don't have compiler bugs. I hope you don't hit compiler bugs often enough that this is a big issue, that this is really worth doing. I mean, maybe it is. Maybe it depends on your job. If that is your job, then I hate your job. So I think, it's actually probably pretty doable, right? Like if someone said, I'll give you a bunch of money if you provide that, we would provide it very quickly. Yeah, no problem. I don't see a problem doing that. I don't think it would be useful. I think it would hardly ever be useful for most people. But it might, if it's useful, we could totally do that. Yeah.
So there is no future when Pernosco will be open source, right? That's.
I wouldn't say there's no possible future. I mean, RR is open source, and we're keeping it that way. And a lot of our energy is actually spent on improving RR. So there's a bunch of open source work going on. But the Pernosco stuff, the Omniscient side of it, we haven't figured out a business model that works with open source. In fact, we haven't figured out a business model really that works at all yet. But we I think we have a better chance of it working with a closed source solution. If we had enough money, if we had the resources, like I can imagine a world where we have a bunch of resources and we have a lot of users and we provide services and it's all great, and we also provide the tool open source, you can run it yourself. I mean, one thing about it, it is incredibly resource intensive. You can't really run Pernosco on your laptop. There's actually you actually do want infrastructure in the cloud running all this, doing all this heavy lifting for you. And so there's actually an opportunity to make money, even if it was open source. I just think that that's too far out to really commit to or anything like that.
The reason I'm asking is that to me, it seems like there's a mass of interesting research questions and projects one could build with this tool.
Yeah, there is. Yeah.
You know, it's like really exciting, but yeah, I understand that there has to be a business case to just keep on developing it. But if there was a way for researcher to contribute,
well, there's a couple of things we could do. I mean, there's some things we could do there. Like one thing is we could provide an API. Our client is a web client and actually does these queries to our server, which basically does the kinds of things you can imagine. Like when was this executed? You know, where does that come from? Blah blah blah. And anything you want to build on top of that, you could probably build on top of the query system without us exposing anything. In fact, there's one crazy Mozilla user who has actually built his own sort of API gateway by hacking into the client, which is great, right? As long as we don't have to support it. But people can build stuff that way, and I think we'd be totally open to that. And then I can imagine doing, you know, sort of essentially free licensing. It wouldn't be open source, but we could give people access to do things. And one piece of the puzzle is, you know, one piece of code that we have is we have this instrumentation engine that does binary instrumentation of RR replays. I don't know if that was clear from my talk, but it should have been. But that's really what Pernosco is based around. So it's a bit like Valgrind, or one of those tools, and you can write your own instrumentation passes in it, and then they run on RR replays. You know, not the recording. It's kind of transparent. Like we preserve the exact replay. Of course, you have to. That is something I'd like to open source at some point. So when we reach some kind of milestone, I'd like to see that out there, and we can get people using that, because that's actually quite nifty. Yep.
Right. So I think we have probably 2 minutes before we should start leaving the room. So any last either questions or comments, Andreas?
I'm happy to comment on Nico's address in the chat, who says that we need to do more experiments with users, and we need better science to actually find out what's going on. And I think this is particularly true for debugging. We do not know enough about what the central problems in debugging are. We don't know enough about people can perceive, and we do not know enough about which techniques of debugging are helpful in which situation and under which circumstances. We need to do more research in that. We need better funding for that. We also need to get to more training on what is essentially here empirical and social studies here, because we are looking at humans, not only programs. And we also need to train our reviewers in the field to value this kind of research, to value work that focuses on humans rather than just trying to crank out the last percentage point out of some benchmark.
That's well put.
Yep.
Oh. If nothing else, last calls.
Rob, do you encourage for people to work with you in industry? Come on, say that. You'd like
do I encourage people to work with me?
Yeah.
Yeah. What do you mean?
Have people work on real problems, don't you?
I want to work on real problems. I mean, I agree with everything you said. Yeah. I mean, that's incredibly important. I think and this is an area where, I mean, in some areas, the real problems are kind of intractable and not really accessible to academics.
All right. So I think I need to bring this to a close, because in 10 minutes, the next Rebase session with Tudor, Gerba, Alexander Bergel, and Oscar Niestrats will start on molding knowledge. and we need to get the room ready for that.
Great.
A little bit of cleaning in the Zoom room and all of what has to happen. So, please stay on. It was great to have you. Thanks a lot for the discussion, the talk. It was really very, very enjoyable.
Good. Thank you very much, guys. I really enjoyed it. See you later. Bye-bye.
Bye.
Enjoy the day. See you. Bye-bye.
All right. So, Philip?
Yes.
So now you can take over if you wanna.
Okay.
Yeah. Or yeah. I mean, I'll be around, but I guess it's better if you're the host.
All right, and you will stop recording now, and